Hi everyone, I thought I'd do a video on nominal rates of interest. I'm going to try to do a kind of, one of these mind maps. You just do little items and then arrow to another one and then going somewhere else and all that sort of thing. In theory they sort of that writes important processes in your head. I don't know if it works or not. So I've certainly done it from time to time and find it did help generate ideas, especially in exams and things like that. So here we go. Right, let's start in the middle. I've written it down here, so I'm going to try to translate it onto the computer now. Right, so let's start with IP. Okay. Right. So that is an annual rate of interest payable P3. So this is the, and I thought I'd add it in at the end, nominal annual rate of interest. Or we could put it in there. And cross that there. So you can see what I'm doing there. I'm just showing you the flexibility on what we're doing. The key thing is though, it is an annualized rate. Okay, right. Where does my arrow go now? So what does this mean? Well, this means that interest compounds each P period. So let's do a little example on this. I think that's what that one's doing there, yeah. We'll go upwards on this, because this space. So say we've got time 0 there and time 1 there. I'm going to do 0 and 1 there. We'll see what I've got on top of it in a minute. So say we've got an effective rate of interest of 10%. So you can see that at time 1 it's accumulated to 110. Now what we're saying, if we had an interest rate of 10% which is payable half yearly, so P equals 2, there we go. The 5% interest compounds at time half. Remember, there's two payments. We're split now into two. So what happens is it does that. So 1.05, 1.05. Now what that means is the interest is added at that point, and therefore it earns interest from there on. So what this means is this implies that I is 1.05 squared minus 1, which I think equals 10.25% effective. So you can see that the effective interest rate for this nominal rate, 10% payable half yearly, is higher than the annual rate. Here we just get that one jump. There's no added. The interest doesn't earn interest until we get to that point there. Then it's added and then that will earn interest. So what does this mean? I'll do the implied backwards there, which was I don't think I've ever done before, but there we go. I'll put like your arrows like that, I suppose. So what that means is as P increases, the effective interest goes up. And the limiting case is for the delta. So where we have the force of interest, that means where delta is equal to I infinity, and if you remember that equals log 1 plus I. So I'm just doing that so we've got them formulas there. Okay. So on that one, let's try, in a similar vein to this, I'll just quickly change to red because otherwise it's going to get even more muddled. Let's do, so now we've got delta equals 10%, which is per annum convertible continuously. And that implies I equals e to the 0.1 minus 1. And I haven't got my calculator with me, which is rather difficult. Yeah. You see, I put my my piece of paper together with what I'm going to talk about, and then I go off it straight away. So there we go. Right. So let's do e 0.1. Oh, let's turn it on. E 0.1 equals minus 1, 10.52. So 10.52% effective. Okay, so you can see it's bigger than 10% again, and that would be a limiting case. Okay, right, so where have we gone now? We've said, and I'll leave it in red for a minute, we've said for IP equals 10%, the effective rate follows this pattern. So delta is bigger than I365, is bigger than I12, is bigger than I, is bigger than I payable every 2 years, etc. This is all about when the interest is added. So I know I've brought in this concept of the annual rate, which is payable every 2 years. So once again, the principle is it's payable every 2 years. So the interest doesn't earn interest until 2 years. So of course that's going to be a smaller effective rate than an annual rate. Okay. I then thought I'd say, well, actually I've done a derivation. This is a little bit jumpy because I've done quite a lot of detail here. So derivation of delta from nominal rate. Okay, so what did I do? So first of all, we use Euler's rule, which hopefully you can remember is limit where n goes to infinity, 1 plus x to the n over n, and then that tends to e to the x. Okay, right. So what do we got? Actually, I missed that. Got 1 plus I equals 1 plus I. We're going to derive this as well. I must have missed this on one of my, I haven't got my glasses on today. So if you remember up here, You can see our effective rate there. So 1 plus I is equal to what the nominal rate broken down into an effective period, which I'll talk about in a little while, and then to the power of p there. Good. So we've got this. Now we're going to apply Euler's rule to that. We're going to say the limit where p tends to infinity, 1 plus I to the p over p to the p, which is equal to, tends to e to the I infinity, and we'll define that as delta. So it implies we've got 1 plus I equals e to delta. Right, now, okay, so I've done that. It's slightly out of order. Other bits to do now as well, so apologies for that. Let's see if we can find where we've gone there. Okay, right, we're going to go downwards. We're going to change to blue. So let's go down here. So one of the fundamental results that we use is I to 1 over p equals I to the p over p. Now you have to be a little bit careful with this definition once you get out in the real world. Some people use this, some people don't. So this, to be clear, is the effective rate per p period. So if we put this on some sort of timeline, so once again we'll use the old p equals 2 example. So we've got time equals 1, time equals 0. So we've got we've got I2, and I2 is an annual amount, but remember it compounds every half year. So we divide that amount by 2. So we do I2 over 2, and that equals our effective rate per half year. Now we've got our effective rate, we can do our compounding. So we can see what we've done here is 1 plus I to the half squared, and that gives us our annual equivalent. So remember, I've used that over when I went to derive delta over here. Remember, I've done it slightly at the wrong time. Okay, so we've got a nice relationship here. And of course we can generalise this. We can change the p equals 2. We can just plot back in 1 plus I to the 1 over p to the p equals 1 plus I. And then we can swap that back out as well. 1 plus I to the p over p to the p equals 1 plus I. We can then rearrange to give I to the p equals p 1 plus I to the 1 over p minus 1, and there we go. There's our nice simple relationship there. Really, I need to cross these off on this piece of paper, really. But there we go. Okay, so we've used quite a lot of room up here. So I think we'll go on to the next part. I think we'll go on to the nominal rate of discount. Okay, so I'm going to file, save as, change that to non-int, some documents, yeah, that'll do. So, I'll do a new file, new, should pop up, yep. So, nominal rate of discount, right, okay, so DP. There we go this time. So if we remember from nominal, rates of discount, effective rates of discount, they are governed by this formula here. So present value equals 1 minus the effective discount rate to the t. What have we done there? On the timeline, there's time t, there's a cash flow of 1, and then we're now discounting that to time 0, so we multiply by 1 minus d to the t. So conceptually, that's how we think about that, okay? Now why do I conceptually think about present values? You must be thinking that. You must be. Well, it's because present values are an action which requires effective rates of interest, and effective rates of discount. Remember, we can only discount or accumulate with effective rates. We can't do it with nominal rates. And of course, a present value is a present value. So if we've calculated a present value using an interest rate, if we find that same present value, we know that we can equate this with our effective rate of discount, which is what we've done here. So I introduced that as a common concept, the common concept of present value, which governs, quite frankly, everything we really do. Everything we do is built on that fact of effective rate of interest or effective rate of discount, and what's going to happen over time with amounts of money, present value. So this is key. Okay, right. So what are we going to go and do with that now? Well, we're here to think about the nominal rates of discount. So, how, in a similar vein to what we've done on the nominal rates of interest, what are we going to do here? Well, so we've got a period, and it says, say, 0 and 1, and it says D4 equals 10%. Per annum. Payable or convertible, sometimes used, payable quarterly. Okay. So we've been given that. So that's 10% across that whole period. However, we know the effective rate isn't taken like that. The effective rate, so now we'll circle around that, well, whatever shape that is. So then we say the effective rate of discount per quarter is equal to 10% divided by 4, which equals 2.5% per annum. 1, 2, 3, 4. Now we're going to use our, how do we use that? How do we equate that? So we've started in nominal world. How are we going to equate this to effective world? Well, we're going to use the present value. So each of these jump backs is 1 minus d to the quarter. 1 minus d to the quarter. And then ditto here and ditto here. Sorry, my pen is getting a little small for that. So where are we going to go with it? Well, we're going to say that 1 minus d is equal here to 1 minus d to the quarter to the power 4. And then we can do some algebra and we can rearrange to dp equals p 1 minus d to the 1 over p bracket. And there we go, we've got our standard result again. So some of you who haven't got time to study this at depth, maybe just trying to revise it for the exam, didn't engage too much during the course, which is up to you and is not atypical, of course, as you'd expect. I was similar when I was a student. You'll be tempted to sort of jump to these formulas. Put all these formulas in your head for the exam and say, right, I've got all these formulas, as long as I use the right one, I'll get all the marks, which might or might not be true. Whereas some of the others who have given yourself more time, you'll realise the concept of using this here. This picture here tells you what you need to know to really understand what's going on and going from the world of nominal rates to effective rates. Okay, let's do some other things. So, what other formulas do we know and love? Well, let's go off here. So you can see we've got our present value thing here. When we're in the world of effective rates of interest, we have PV equals V to the T. And where is 1 plus I to the minus T? Yeah? So let's use that. We'll replace the 1 minus D with the V. So now you can see we've got, from first principles of present value, we've now got a working relationship between the effective rate of discount and the effective rate of interest. After some algebra, where do we end up with? Well, we end up with that, which hopefully we've seen several times. Okay. So we've got our relationship between the effective rates. We can go and form a relationship between nominal rates. I'm not going to do that. You can do that. You've now started to get all the clues that you need to be able to do that. So, a blank off here, and I put the word uses. Where do we use this? Can we remember where we use it? Well, we might use it directly, which is turn into an effective rate and then discount or accumulate. How do you accumulate? You might use it on some assets. Treasury bond. A US bond pays $100 at T equals 3. Market price is, $80. What is D? I've played on it a bit. Usually you're given D, you're given a maturity price. You have to find the market price. So 80 equals 100. 1 minus D. How many years was it? 3. There we go. Not going to do that algebra for you. You can do that. 3 annuities. Remember we're using that. So remember the standard, the annual annuity formulas. So once again, scribble down some formulas. That. And then when there's a double dot, that turns into that. And then when there's a line, that turns into that. That's the only difference. Now let's go to this. Let's have an n-year annuity which is paid peakly. 1 minus v to the n, no change, over I to the p. A double dot p n 1 minus v to the n over e to the p, and then of course no change for that. It was already paid continuously, so there's only one expression. It's just over delta, so no change there. Right, okay. So I think that concludes where I wanted to get to. I think if you could sort of recreate most of that, you're going to have enough to really, really push through in an exam. But more importantly, it should give you the framework to solve problems if you see them in real life. And then of course the other thing is just to aid your understanding of what the concept of nominal rates of interest and discount are, because they're not straightforward. They require some earlier information. You can't use them directly, so you need to see where you've come from with them and where you're going to with them. Simply knowing how to calculate them is nothing. It's just some numbers. So I have to change that. So okay, right. Hope that helps. See you all very soon. See you later.